Okay, so let me conclude here the lectures with a part 3 for simple circuits. Prior to doing so, however, make sure that you take a look at the CK12 work that was posted in today's folder, as well as the next problem set, and note all of the due dates that are associated with those assignments. Okay, so to conclude part 3 here, we're just going to take a look at 2 examples. So go ahead and copy down the first of those 2 examples into your notes. This is the problem involving a hairdryer. Okay, so a hairdryer, it's a resistor, is connected to a 120 volt, that's the RMS voltage for an alternating current line in the United States, and operates at 1000 watts. So this is some of the terminology that we use here when describing alternating current. Okay, so we'll just picture the hairdryer as a resistor, and then therefore we have a simple diagram. It just looks like this. All right, so here's the generator symbol from earlier, and the RMS voltage associated with it is given as 120 volts. Okay, and then here's the hairdryer itself, which is just a resistor R. And then we have the conventional current that is flowing here. It's an alternating current. We write down the average value, however, on a simple diagram such as this. This is called the root mean square current, IRMS. Okay, now the hairdryer itself operates at 1000 watts. So in other words, that's the amount of energy per second that is being delivered to the hairdryer by the generator. So from part 1 of today's lectures, we can write down the expression in the following way. Okay, power equals I times V, like so, where we have the RMS values here for alternating current written in the expression. All right, so now let's immediately calculate the amount of current, IRMS, that's flowing through the hairdryer. Like so. So it's 1000 watts, and then we divide that by 120 volts. We'll end up with a number here that's in terms of amperes. Okay, so the power is 1000, and then divide that then by 120. This comes out to be 8.33 amps. And then what we'll do is use Ohm's law here across the hairdryer to then calculate the resistance R as is being asked for in part A. Okay, so here's Ohm's law. VRMS equals IRMS times resistance R. So I'll just go ahead and take 120 volts here and divide it by the 8.33 amps that we just calculated. All right, so then therefore when I do, so let's see, 120 divided by that, and that comes out to be 14.4 ohms. Okay, this right here is a property of the hairdryer. It's a property of the wiring that makes up the hairdryer itself. None of this changes when you now take this from the United States to Europe. Okay, so this right here on the top board is what's happening in the United States. And now let's go ahead and take the hairdryer here to Europe. Okay, when we do, the RMS voltage in Europe is 240 volts. And then here's what's being asked for in part B. Okay, so in part B, it now asks us, okay, well, what would happen if you take the same hairdryer and you take it to Europe when it's connected to 240 volts instead? Well, let's see what occurs. All right, so VRMS is equal to IRMS times R. It's the same hairdryer, but this right here is 240 volts. So let's now go ahead and calculate the new current that's drawn if you plug it in Europe without an adapter. So divide, like so. So now I take 240 and then divide that by 14.4 ohms. And the amount of current drawn now is twice as much as what it was in the United States. In this case, it's about 16.67 or so amperes. So watch then what happens when I calculate the amount of power that is delivered now to the hairdryer. So the amount of power that's delivered to the hairdryer is the new RMS value here of the current, 16.67 amps, and then we multiply that by the voltage of 240 volts. So multiply that by 240, and this comes out to be 4,000 watts. So in other words, you're delivering 4 times as much energy per second to the hairdryer in Europe as opposed to what you would be doing in the United States. This is not good because if you deliver this much current to your hairdryer, you're probably going to melt the hairdryer or ultimately cause it to catch on fire or something like that. So then therefore, to prevent that from happening, you need an adapter. The adapter is a resistor. It's a resistor that is placed in series with the hairdryer when you plug it in Europe, such that the current then goes down. The amount of current drawn by the hairdryer will then still be equal to 8.33 amps, and the amount of power delivered to the hairdryer will still be 1,000 watts. So that's what you're buying when you're buying an adapter to bring your devices from the United States to Europe. You're buying an additional resistor that is placed in series with the device, okay? Okay, so this right here is just a brief description of a simple series circuit. In this case, I just didn't draw the second resistor, but that second resistor would be necessary as an adapter when going from the United States to Europe. Okay, so the second of the two examples that we'll look at now is a parallel circuit. So go ahead and copy down that problem into your notes. I'm going to go ahead and erase the board and then move it here to my screen. Okay, so this is going to be a parallel circuit problem where you're basically going to be turning on more and more things in your house. Okay, when you do this, when you lower the resistance by turning more and more things on in your house in parallel, this then means that ultimately more current is flowing through your house. If the current reaches a high enough value, then that current could start to melt the electrical wiring. And then if that happens, it can cause a fire, etc., etc. So to prevent all of that from happening, what is built in series with respect to everything else that is in parallel is what is called a fuse. So let me describe that here in the context of this example. Okay, so 4 circuit elements consisting of a 100 watt light bulb, an 1800 watt electric space heater. Space heaters, by the way, are a little bit dangerous, so be careful with them. A 350 watt stereo and a 1000 watt hairdryer are all connected at your house in parallel to a 120 volt line. Now I'm just going to draw this as a battery symbol as opposed to the generator symbol, so we can kind of drop the RMS notation here and just use the notation of direct current from earlier. It's perfectly fine in this example. All right, so right here is going to be our battery, if you will, with the voltage V equal to 120 volts. Okay, and then right now I'm only going to hook up a single item first, which has a resistance R1 associated with it and a power that is delivered to a P1. This is the 100 watt light bulb. Okay, now placed in series with all of this, however, let me draw it right here, is this circle symbol, is a fuse. The fuse itself is typically either a thin piece of metal that will melt and break the circuit if the current is high enough, or it is a switch that is formed from what is called a bimetallic strip. I'll explain what that means in just a few minutes. Okay, then we're going to have a conventional current I that is flowing through the circuit. Okay, let me go ahead and calculate how much current I here is flowing through the circuit by just simply doing the following. Let's go ahead and find the resistance here, R1, by doing the following expression. P1 is equal to V squared over R1. Remember that the voltage across this resistor is the same as the voltage across the battery, because this right here is an equipotential surface, and this right here is an equipotential surface. So let me go ahead and cross multiply and calculate R1. Like so. And now that resistor then, the resistance itself is the following value. So 120 squared and then divided by 100 watts. And this comes out to be 144 ohms. And then by using now Ohm's law, I can now go ahead and calculate the current I. So V equals I times R1. Let's now go ahead and solve for the current I. So it's going to be V over R1. Okay, so 120 and then divided by 144, and this comes out to be only a small amount of current, 0.83 amps. And now we start to add things in parallel, and then I make the same types of calculations here as I go. Ultimately, our goal is to calculate the total amount of current that is flowing through the circuit as we turn more and more things on. As we'll see, that number is going to go up. Okay, so next we turn on the 1800 watt electric space heater in parallel with this. I'm just going to draw another diagram to illustrate. Okay, and here's my fuse once again. Okay, now we've got here R1 from earlier, and now R2, where the power that's delivered ultimately to the electric space heater, P2, is given to us as 1800 watts. Okay, here's the current I, and then we get the junction rule again. We're going to have an I1 flowing like so, and an I2 flowing like so. The I1 that is flowing through this resistor, the 100 watt light bulb, is exactly the same as we calculated earlier. It's 0.83 amps. And now, let's run through the same sorts of calculations here in order to calculate the amount of current I2 that is flowing now through the space heater. We'll then add it to this value to get the total current I from junction rule. Okay, so let's find the resistance first. I'm going to go ahead and do this calculation here. So the resistance of the space heater R2 is going to be the voltage squared divided by the power P2. Okay, let's go ahead and calculate that value. Okay, so 120 squared and then divided by 1800 watts. And this comes out to be 8 ohms, like so. And then from there we can now go ahead and calculate the current I, and in this case it's I2. So it's going to be the voltage V divided by R2. So the voltage V is once again 120 because this is a parallel circuit, and then divide by 8. And this comes out to be 15 amps. So notice that the current that's being drawn is really starting to creep up here as we turn more things on. Therefore, the total current I is now I1 plus I2. So the total thus far is 15.83 amps. Okay, next you turn on the stereo. So I'm going to add a branch then to the circuit. Like so. So here's my battery of voltage V. Once again, here's the fuse. I keep on forgetting to draw it. Like so. Here's the current I. And now the current splits into an I1 through the light bulb, the I2 through the space heater, and now an I3 through the stereo. The I1 is the same thing that it was before, 0.83 amps. The I2 is the same thing that we calculated a few minutes ago, right here, 15 amps. And now we make the calculations here to find I3. In order to do so, we first of all have to find the resistance R3. We'll use this expression here once again. P3, by the way, I forgot to write it down for the stereo, is given to us as 350 watts. Okay, so now R3 we'll call it, is V squared over P3. So this is going to be 120 squared and then divided by 350 watts. This comes out to be 41.14, give or take, ohms. And then from there we'll be able to calculate now I3. So I3 is going to be V over R3. All right, so 120 volts and then divided by that resistance, and this comes out to be an additional 2.92 amps. So the total amount of current I now that's flowing through your house is I1 plus I2 plus I3. Once again, that's junction rule. So then therefore I have 0.83 plus 15 and now plus 2.92. Okay, this is 18.75 total. When you have this much current that is flowing through your house, this then means that your wires are really starting to heat up. This is where it starts to become dangerous. And now you make a mistake and you turn on your hair dryer, your 1000 watt hair dryer, for example. Like so. So now you've got 4 things on at the same time. So we still have here R1, here's the fuse again. Here's the current I. We still have I1 flowing through. That's still 0.83 amps as it was before. Okay, here's the R2. with the I2 flowing through that, that's still 15 amps, just as it was before. And then we've got here now I3 from earlier flowing through this resistor. The I3, remember, was the 2.92 amps. Okay, but now we're going to have here an I4 that is flowing through this device. Okay, this last device here, the hair dryer, has a power associated with it equal to 1,000 watts. So now let's go ahead and find the resistance R4. In order to do so, we'll use this expression here once again. So R4 is equal to the voltage squared divided by P4. Okay, so 120 squared, and then divide that then by 1,000, and that comes out to be, wrong number, try that again. There we go. 14.4 ohms, like so. And then we'll take that number, and then we'll go ahead and find then the current I4. Okay, so I4 is equal to the voltage divided by R4, so 120 over that. And that comes out to be 8.33 amps. Obviously now the total here, the total amount of I is going to be greater than 20 amps. So I1 plus I2 plus I3 plus I4. So we're going to take here the 18.75 amps of these three guys from earlier and then add to it the 8.33. So 18.75 plus 8.33, and sure enough this is much greater than 20 amps in this case. It's 27.08. So this is dangerous. So because this is dangerous, then the fuse that you have placed in series with all of this is good. Because at this point, for example, this small piece of metal here would melt. When it melts, it then breaks the circuit and everything turns off and nothing catches on fire. Now, in your actual house, what they have in your house is a fuse box, usually outside, where you have all of the fuses themselves. Okay, what happens in that case is what's referred to as a bimetallic strip. The bimetallic strip is the fuse itself, and it consists of two pieces of metal that are fused together side by side. When these two pieces of metal heat, one of the pieces of metal expands faster than the other. This then causes the bimetallic strip to begin to curl, like so, in this direction. And if it curls enough, boom, it breaks the circuit and it turns everything off. And then your father, for example, has to go outside with a flashlight if it's night, and he then has to go outside to the fuse box and basically flip the switch back into the opposite direction, like so, after it's cooled. Prior to doing that, however, you have to make sure you turn everything off in your house. And then once you've turned everything off, then he goes outside and he flicks the switch back into its proper position such that you can turn things on once again. So this is a nice example here of a parallel circuit to conclude this lecture. Make sure, once again, that you take a look at the assignments and their due dates, please. Today's shirt was Funebrarum. Be safe, everybody.